Buddy, my name is Tyler Dick, and welcome to the virtual W. Hay Railroad Engineering Seminar. Before I introduce our speaker, I'd like to remind all of our listeners that you can ask questions using the question box to the side of your screen, and one of the moderators will read it to our speaker at the end of the presentation. Also a reminder that although the presentation and seminar is scheduled for 1 hour, we may continue past 1:30 p.m. Central Time here to answer some additional questions if needed. If you need to leave and log off, then that's fine as well. The William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. On behalf of all of us, we thank the Association of American Railroads, BNSF Railway, CN Railway, Hanson Professional Services, and Union Pacific Railroad for their ongoing support of RailTech. It is greatly appreciated by those of us here on campus, as well as those of us participating via the internet. I would also like to extend a welcome to the over 200 people who registered for this seminar, representing over 13 different countries around the world. This list includes representatives from freight and passenger railroads, transit agencies, federal and state departments of transportation, engineering firms, universities, research organizations, technology developers, suppliers, and many others. We are very pleased that you can join us for what I know will be a very interesting seminars. For those of you who wish to receive professional development hours for your participation in this seminar, please be sure to send us an email to the email that was listed in the seminar announcement with your information for this seminar. This is likely our final Hay seminar for the spring semester, but we are planning to resume in fall 2021. Watch for details via email and on the RailTech website. Our seminar today considers the fact that North American heavy haul freight railways achieve greater energy efficiency and reduced emissions compared to other land transportation modes. However, in the face of rapidly advancing technology to reduce the energy consumption and emissions of highway trucks, freight railroads must continue to advance in both energy efficiency and emissions. Alternative propulsion technologies such as battery and hydrogen fuel cell locomotives to eliminate mobile source carbon emissions raise various practical challenges for changing locomotive propulsion technologies across the integrated, interoperable North American freight railway network with its fleet of over 29,000 long-lived locomotive assets and associated servicing infrastructure. Our speaker today to discuss this topic is locomotive and railroad technology consultant Michael Iden. Mike retired from railroad deployment in late 2018, having worked for 3 railroads, Southern Railway, Chicago and Northwestern, and Union Pacific, for a cumulative total of 42 years. He also worked at locomotive builder Electromotive Division of General Motors for 3 years. Much of his railroad career was devoted to new locomotive designs and technologies, including implementation and adoption of AC traction, Locotrol for distributed power, and responsibility for the earliest efforts with ultra-low emissions locomotives, such as diesel, battery hybrids, and multi-engine switchers. He currently advises various railway clients on locomotive technology deployment through his consulting company, Tier 5 Locomotive LLC. Mr. Iden has a Bachelor of Science degree in Mechanical Engineering from the Milwaukee School of Engineering and a Master of Management degree from Northwestern University. And he is also a registered professional engineer in 3 different states. I've had the pleasure to learn from Mike and his experience on several research projects here at the university, and I'm very pleased to introduce Michael Iden to present his seminar entitled The Dual Challenge of Decarbonizing and Improving the Fuel Efficiency of Freight Railroads. So Mike, please take it away.
Okay, thank you, Tyler. Good afternoon to everyone. And as you can see from the title slide, we'll be talking about 2 things, decarbonization and increased energy efficiency. First, a simple disclaimer. The comments expressed in this, other than some media quotations, are mine. And I am not endorsing, approving, or rejecting any particular technologies, any designs by any specific manufacturers, and am not criticizing any manufacturers, railroads, or organizations. Again, these are my own comments, and any errors in assumed calculations and assumptions about results are solely mine. So with that, Emma, if we could have the first slide, please. We'll be talking about these 7 topics: decarbonization, where we've been and what's ahead for railroad energy, seeing what's next for decarbonizing railroads. We will look at propulsion, energy, and infrastructure alternatives for the future. Some closing thoughts, some recommendations, and a slide about what I refer to as managers' misconceptions regarding technology. Next, Emma. And some key definitions. The key one here, efficiency. It's the ratio of useful work or applied energy to the total energy expended in producing that work. And we'll move on here, Emma. And decarbonization. I think everybody knows about decarbonization and the attempt to reduce and stop the growth of carbon in the world's atmosphere and the issues that are driving it. We're not going to be talking about global climate change and so on. We'll be talking about decarbonization. Next slide. There are various plans to address the global challenge of carbon. And what I'm showing you here is one of them. It's a report issued by Princeton University. It's called Net Zero America. I have the web link shown. It's a 365-page report. I've not read the report. I have gone through it to get a feel for what they are talking about. It actually contains 5 different plans, depending on things like having carbon capture and sequestration versus not having CCS. And again, it's actually 5 plans within one. And this plan actually is talking about the need to invest $2.5 trillion over the next 9 years. It basically calls for achieving what I'm going to show you next by 2030 to set the stage for 2030 to 2050, converting to, for example, zero emissions vehicles. And if we can move on to the next slide, Emma. And this graphic basically shows where the $2.5 trillion would be invested in general, depending on which plan you're looking at. And I want to point out here that this is so massive. They note that there is a $10 billion rounding error allowed in their calculations. But you can see they are talking about having 55% of the investment over the next 9 years going into electrical generation, transmission, distribution, and electric vehicle charging. So more than half of the $2.5 trillion would go into electrification. And we'll move on here to the next slide. This is from an article in the New York Times recently. The map in the upper right shows, according to one of the net zero plans, where wind farms and solar farms would have to be located by 2050 to accomplish the net zero plan, along with zero emission vehicles and changing homes from gas heating to electric heating and so on. The blue areas are where wind farms would be located, and the orange are where solar farms would be located. And Emma's moving that dot. That's roughly the location of Urbana-Champaign, where UIUC is located. And what struck me in looking at this map is that almost the entire state of Illinois would probably be not necessarily blanketed, but it would be a ground zero in effect for a massive number of wind farms. In the lower left, you can see a map that shows wind energy potential. It's greatest in the western US, but to the right of it is a map with white areas where wind farms are not easily constructed because of things like mountainous terrain. So you can see that there are a number of factors here involved in where wind farms, for example, would be located. Next slide, please. And the 2 maps at the top are again from the Princeton Net Zero Plan. The map in the lower right is from an alternative plan from Bloomberg Green News. And the Bloomberg Green Plan calls for 44% of electricity be from renewable wind and solar, and 50% from a combination of gas turbines using renewable methane and an additional 250 nuclear power plants. So again, I'm just showing you this because of the plethora of plans that are out there, in addition to the administration's own plan for infrastructure, which includes renewable electricity, but is not necessarily limited to some of the things that these private plans are talking about. And next slide, please. And three headlines from the recent news media regarding the global maritime industry. I didn't realize it until this morning. The global shipping industry is not included in the Paris Accord. Global shipping comes under the guidance and control, so to speak, of the IMO, the International Maritime Organization. And global shipping was specifically exempted, according to an article in today's New York Times, from the Paris Accord because of the transnational nature of maritime shipping. You can have a ship, a container ship that's built in South Korea. It may be owned by a Taiwan corporation based in Taiwan. It may be chartered by an American company with a crew from Asia and hauling freight to Europe. So it becomes a maritime shipping is highly complex. But there's an article on page 1 of today's New York Times, if you have availability of it or on the internet. It's an interesting article talking about some of the difficulty within the IMO in making decisions about decarbonizing that industry. And what's important, I think, on this slide is the green comments at the very bottom of this slide, the last sentence, the quote. First, you need the fuels, then the necessary volumes, and a global bunkering network. That is the infrastructure for maritime shipping that will all have to come together at a competitive price, obviously talking economics. We're only at the start of a long and expensive process. And what I find so interesting about maritime shipping with the large container ships, the very large crude carriers, bulk ore carriers, and so on, those ships are basically engineered, designed, and manufactured and financed for a 25-year life. And at the end of about 20 years, they go to the ship breakers in Asia and they get torn down, and the steel and so on all gets recycled. But they only have a 25-year life. And there's roughly 60,000 large ocean vessels. We have locomotives that are designed for an initial, the first engine life of no more than a decade. We overhaul the engine, and the locomotive could be re-engined and overhauled many times over several decades of life. So there's some commonality with maritime shipping, but also some great differences vis-a-vis the railroad industry. And next slide, please. And just some key points here. Decarbonization, all of these plans are to eliminate the use of fossil fuels. Any liquid fuels, for example, that would remain in use would be they would be considered renewable. You would not be emitting more carbon than is being reclaimed. It would be to increase electrical transmission to accommodate the variable productivity of both wind and solar. Wind doesn't always power turbines all the time, and the sun obviously doesn't shine more than about 60% of the time, depending on the time of the year and where you are on the planet. So you have to be able to eliminate and replace fossil-fired generating stations, for example, that could theoretically be operating 100% of the time until they go into an overhaul maintenance cycle. It also is to develop and install large-scale energy storage. Batteries, for example, that can store wind and solar power to be reused when the wind may not be blowing in a certain area or the sun is not shining. It is to enable the manufacturing of zero carbon hydrogen. And an important point that we all need to keep in mind, even though hydrogen, when it's used, for example, in a fuel cell, you have a zero emissions point source. But currently, for example, 95% of all hydrogen that is manufactured in the United States comes from steam methane reforming, which is a process where you burn natural gas to produce steam, and you mix natural gas and the steam at high temperature and pressure and pass it over a catalyst to strip the hydrogen from the carbon or from the methane molecules. So currently, manufactured hydrogen is not zero carbon itself. And at the bottom, for transportation, it will drive extreme emphasis on vehicles the fuel or energy source, and the infrastructure to keep those vehicles running. Bottom line, net zero, in my opinion, won't be simple, it won't be easy, and it may not necessarily be free for anybody or most users, even though the net zero plan says that private individuals, homeowners, and so on won't see any major increase in their utility bills. So there are a lot of unknown unknowns in all of these plans. And next slide, please. Okay, now we're going to transition to railroads and energy, where we've been and what's ahead. If the photo that you're looking at looks fuzzy and shaky, it's because I took it from the cab of a locomotive working uphill through a long tunnel, and I had a very slow shutter speed, and so the image is very shaky and it's out of focus. And I think that's an appropriate image to introduce what we're talking about here, particularly what's ahead for the railroads with respect to energy. Next slide. The Sankey diagram that you see in the upper left is from the Lawrence Livermore National Lab of the Department of Energy. Lawrence Livermore produces this Sankey diagram every year. This is the diagram for 2020, showing all of the estimated energy production and consumption in 2020, last year. And you can see, according to Lawrence Livermore, we generated roughly 92.9 quadrillion BTUs, which is the equivalent of about 668 trillion gallons of diesel fuel. And the Class 1 railroads in 2020 used roughly 3.4 billion gallons, which is about 0.47 quad. And you can see that black arrow in the middle of the Sankey diagram. That's pointing to a biomass line of biomass energy going up into residential heating, and which is about 0.48 quad. That very slim, slightly green line is equivalent to the railroad freight railroad energy use in 2020. So again, we're only 1.5% of all U.S. energy consumption, and only 1.9% of the total petroleum that was used in 2020. And again, on the far right, overall, we end up losing or wasting 67% of all energy used, and that's due to the inevitable inefficiencies. No process of using energy is 100% efficient. The most inefficient process in general is currently transportation, and that's largely because of gasoline-powered automobiles, where 79% of the energy in general for transportation ends up being rejected energy. It does not generate useful work. Next slide, please. And the two graphs on the left are from a paper that I wrote and published through the ASME, American Society of Mechanical Engineers, in 2019. I did a 95-year retrospective look at freight railroad energy use in the US. And the red line in the top graph prior to 1960 was the total energy used. Basically, I took all of the coal, crude oil, electricity, and a small amount of diesel fuel that was reported to the Interstate Commerce Commission prior to 1960. And every 5 years, I converted it all to diesel gallons equivalent. And you can see the peak year for railroad use of energy used by the railroads in the US, freight railroads, was 1945, the last year of World War II. And in that steep decline in the red line from 1945 to 1960 reflects the dieselization of the railroads. And essentially, if we can click again, Emma, what we saw was basically a one-time 700% improvement in what we call fuel efficiency, gallons per thousand gross ton miles, due largely to the improvement by eliminating the gross thermal inefficiency of steam locomotives. And over the past several decades, fuel efficiency has been improving only modestly. One more click, Emma. Thank you. And this is from a presentation that Southwest Research has presented to all 7 of the Class 1s. You can see that the industry for the last 20 years or so has been making about 1.5% improvement each year over the last 10 years since 2011. And by my measure, I saw about a 1 to 1.5% improvement overall in gross fuel efficiency from 1960 to 2015. So if you take a 1.5% improvement in fuel efficiency and you compound it out to 2030, we should see about a 20% improvement in fuel efficiency. But the question we all have to ask is that enough? And I think the answer clearly is no. Next slide, please. Okay, railroad energy efficiency improvements. There are many potential improvements, modestly small. There are no big, super, silver bullet efficiency improvements here. But the point of this slide is that there are a number of efficiency improvements that could and should be implemented, and they should be implemented as soon as possible. Now is the time to take advantage of improvements that we can make without any massive investment in new fuels and new technologies. And just one example here on the right, this report again, this goes back to the report issued by Southwest Research. It was created by Steve Fritz from the Institute, along with Wayne Kennedy, who was a former co-worker of mine at Union Pacific, who's now also in private consulting. And this report overall was issued over the past several months to all 7 of the Class 1 railroads. But the example given here is that according to the testing done at Southwest Research at the Locomotive facility in San Antonio, we could improve the net traction specific fuel consumption of locomotives just by addressing air leaks on locomotives themselves. And when you expand this to eliminating air leaks on all trains, not just the locomotives, but the cars, the fuel efficiency improvements and the fuel savings would be even greater. So now's the time to focus on these low-hanging fruit efficiency improvements, again, before we start looking and grasping with much larger, more complex technological changes. Next slide. Okay, alternative fuels. There are trade-offs with alternative fuels. For example, going from petroleum diesel to B20, 20% biodiesel blended with petroleum diesel. You can reduce your carbon dioxide, so you're reducing your carbon emissions. Your PM or particulate matter emissions will go down. Your NOx emissions may go up slightly, and your overall energy content will go down on a volumetric basis. So you're probably going to have to burn slightly more volume of the fuel to perform the same amount of work. And this rolls down into, for example, what are you going to be paying overall on an equivalent gallon basis or equivalent number of BTUs for your overall energy? So there are no silver bullets here with alternative fuels. There are multiple options, and in some cases you will reduce certain emissions, and in other cases you'll reduce some but not all. And in many of these situations, you actually will end up using more volume of fuel. So again, this is a very complex alternative that needs to be looked at carefully, but it's one of the early, as Steve Fritz puts it, it's one of the early control knobs that the railroads could exercise and use to reduce their carbon emissions. Next slide, please. Okay. I want to mention again, I've mentioned this several times in industry presentations. We all need to be aware of what's coming with heavy duty trucks with the efficiency improvements. Starting in 2010, the Department of Energy here in the US and the truck industry, manufacturers of tractors, trailers, truck and tractor appliances, transmissions, engines, etc., spent $284 million focusing on aerodynamic improvements for trucks. That was called Super Truck 1. That was followed by another program called Super Truck 2, which ended in 2020, and that was a $160 million investment. And now Super Truck 3 has been announced. It's another $200 million. So over the next several years, the total spending on truck efficiency improvements will total $644 million. Half of that from the federal government, half from the truck and truck suppliers. Next slide, or next click, Emma. And in addition, platooning, which is the close coupling of trucks with about a 12-foot gap between the trucks where you have vehicle-to-vehicle control, that will gain heavy-duty trucks another 7 to 10% improvement in fuel efficiency. And the last click, Emma, autonomous control of trucks by eliminating driver variation is projected to improve mile per gallon fuel efficiency for heavy duty trucks by another 10%. And you'll note what I've put at the bottom. The driver you see here without his hands on the wheel, he's passing through Champaign at this very moment at 55 miles an hour, watching this HAY seminar on his iPad as the autonomous level 4 control is moving his truck along. Next slide. Real quickly, truck technology is moving ahead very fast. The large truck fleets typically refresh. They renew their tractor fleets every 2 years. I'm talking about companies like Schneider, Werner, Swift Transportation, and so on. And Too Simple, one of the companies in the autonomous world for trucks, they are partnering with Navistar to sell high automation Class A trucks by 2024. And they gave the example of a 951-mile movement of fresh vegetables from Arizona to Oklahoma City. It currently takes 24 hours. If you have one driver, it takes 24 hours because the driver has to have 10 hours of rest, whereas the autonomous truck could make that movement in 14 hours. So we're talking not only efficiency improvements, but an impact on competitiveness vis-a-vis, for example, the rail industry. Next slide. Okay, seeing what's next to decarbonize railroads. And again, the past is a good predictor of the future only when conditions in the future resemble conditions in the past. Next slide, please. Okay, back in 1950, there were 127 Class 1 railroads. Today, there are 7. Obviously, the requirements for what is a Class 1 railroad have changed, largely greater amounts of revenue. Back in 1950, we essentially had 3 national networks, a US network, a Canadian network, and a Mexican network, with a small amount of cross-border traffic. Today, we have one integrated continental network with a large amount of rail traffic and equipment moving across both borders between all 3 countries. Next slide. All right, steam to diesel was essentially 1940 to 1960. It was a 20-year process, but it was preceded by 20 years of research and development and preparation. And what I see here is we've got probably 9 years to get ready and then 20 years to implement if we're going to do something involving decarbonization. So, you know, the challenge is probably going to be even greater than what happened. And the key point here, one reason largely why the railroads decarbonized or why they converted from steam to diesel from 1940 to 1960 is that the massive fleet of steam locomotives was largely obsolete and worn out by World War II. So there are a host of differences between the steam to diesel era and what we may be looking at. Next slide, please. Okay, the economics of railroad dieselization. This is from a paper that was published in 1951, giving 6 reasons why the railroads decarbonized. Thermal and energy efficiency was several times greater. Availability took a huge increase. Tractive effort was higher with diesel locomotives compared to even the biggest steam engines. Dynamic braking was created. Repair costs were half that of steam, and the modular design of diesel locomotives allowed eliminating the assignment of specific locomotives to specific trains. 5 of these 6, next slide, 5 of these 6 reasons for dieselization, we're not going to be able to book them again. The only one we're going to be able to book potentially is thermal efficiency advantages going to some of these alternatives, because a lot of these things they've already been rolled into the economics of railroads as we know them today. So we won't be able to count a lot of these things in our economic analyses. Next slide. Okay, carbonization, how it may change the railroads. First of all, we've all become comfortable with and increasingly dependent on what I call universally usable high horsepower diesel electric locomotives. In that top photo, you can see a Ferromex locomotive from Mexico and a Norfolk Southern unit at Union Pacific's Proviso Yard here in the Chicago area. Another question at the bottom, if a railroad in the future, let's say Railroad A, chooses to use one technology to decarbonize and Railroad B chooses another technology, but they both have joint line operations where they operate directionally on each other's railroad, what will the railroads do? What if one railroad opts for, let's say, hydrogen fuel cells and the other opts for electrification or battery electric locomotives. How will the railroads meld these alternative technologies together? Next slide. What I'm showing here is, I call it a hypothetical railroad, and I'm simply stating here that it may come to be based on economic analysis and the availability of energy, such as where decarbonized electricity is most readily available and the economics are favorable. It's possible, in my opinion, that there could be some sections of a railroad that would be best suited for straight electrification, other areas that would be best suited for the use of hydrogen fuel cells, and some areas where battery electric locomotives may be most favorable. And the ratios could shift depending on the nature of the traffic, the size of the railroad, the configuration of terminals, and so on, and train movement. But again, the future, I think, again, going back to that shaky, fuzzy tunnel photo, the future is a little shaky and a little fuzzy and unclear. Next slide, please, Emma. Now we're going to talk about some specific alternatives for propulsion and infrastructure. Next slide. Okay, the incumbent technology is diesel electric locomotives. So again, we take a liquid fuel, convert it to mechanical energy in an engine, to electrical energy in an alternator, and we go from AC to DC, pass it into inverters, create a synthetic AC for AC locomotives, and we produce work, and any dynamic brake energy is lost as waste heat. The key point here is at the bottom. We have compatible operation across a continental network in 3 countries. We have a compatible parts supply, maintenance skills, and facilities. We have compatible refueling infrastructure, and we have compatible and universally available fuel, either petroleum, diesel, biodiesel, or some renewable, and it's all available via pipeline, truck, barge, etc. Next slide. One of the alternative technologies, for example, is hydrogen fuel cells with batteries. We would be taking liquid or gaseous hydrogen and converting it into electricity and fuel cells, using it to charge onboard batteries or go directly into the inverters to produce AC power at the traction motors, and any dynamic brake energy that's generated could be captured by the onboard batteries up to the extent that the batteries can recapture that energy. Going to the very bottom, however, there is no such operation right now in any of the 3 countries. There's no parts supply, maintenance skills, or facilities. We have no refueling infrastructure. These are all things that will have to be created, acquired, installed, and operated. Again, there is a limited amount of hydrogen manufactured in the US and Canada. Most of it is high carbon. For long haul locomotives, line haul locomotives will probably, in my opinion, need hydrogen tenders, either liquefied or gaseous. And again, I'm pointing out that the locomotives will be a combination of fuel cells and batteries. And we'll talk about that a little later here. Next slide, please. Okay, some brief comments about hydrogen compared to methane. Hydrogen, particularly when it is liquefied, cryogenic liquefied hydrogen, is the second coldest material known to man. The coldest material is liquefied helium, which is just 7 degrees greater than absolute zero at minus 459 degrees Fahrenheit. You can see that liquefied methane is about 260 degrees below zero Fahrenheit, and liquefied hydrogen is 423 degrees below zero. Hydrogen is exceptionally light and not dense compared to air. It only has 7% of the density of air, whereas methane gas is 55%. It's much heavier. And a key point here, and I'm simply pointing this out, I am not anti-hydrogen, but I want to point out some realities here. The flammability range for hydrogen is 4 to 74% by volume mixed with air, whereas methane gas is flammable between 5 and 14%. And the minimum spark energy for ignition is 2/100ths of a joule, which is a measure of energy, and that is 1/14th of the spark energy needed to ignite methane and air mixture. And it's been documented, for example, that dust particles in a vent stack, the static electricity generated by dust particles flowing up a vent stack have been sufficient to ignite a hydrogen gas and air mixture. Hydrogen as a locomotive energy carrier will be subject to the FRA's requirements here in the US for gaseous fuel safety analyses, authorization from the FRA for use, and so on, dating back to 2014. And I've got a photo there of a compendium which was funded by the FRA to support the AAR natural gas fuel tender technical advisory group that operated from 2011 to 2017, and we generated the first interoperable standard for locomotive tenders. And the FRA was kind enough to fund a compendium of national and international codes, standards, and regulations applying to natural gas, many of which would apply to the use of LNG or CNG here in the US and Canada. And my opinion, this type of document needs to be updated to expand it for codes, standards, and regulations relating to the use of hydrogen. Next slide. And talking about infrastructure and rolling stock needs, the photo in the upper left, that shows a double LNG tender refueling of a fuel tender on Canadian National. It was actually a tender that was leased from Union Pacific, and CN was delivering about 16,000 gallons of LNG to the tender in Edmonton, Alberta. And in the same tender, after it was returned to UP, we did a test. And you can see a vacuum insulated hose connecting an LNG tender or LNG trailer to the tender. And you can see the heavy frost buildup as we were passing liquefied LNG into the tender. Again, this is the second coldest material on Earth. But the key point here is that locomotive shops will have to be modified for National Fire Protection Association and regulatory codes to accommodate the presence of any hydrogen gas similar to methane gas. And this means explosion-proof electrical devices such as motors, switches, lights, heating fixtures, etc., increased ventilation, etc., unless you bring a gas fuel locomotive into the shop and you know that all of the flammable gas has been purged from the locomotive. So the use of gaseous fuels has a potential to even drive a fairly large change in shop infrastructure. Next slide, please. All right, let's talk about going back to hydrogen fuel cell locomotives. You will likely have a combination of fuel cell stacks in series to add the voltage to get up to roughly 1,000 volts. The fuel cells could provide electrical energy directly to the traction motors through the inverters. And when the traction energy, when less of it is needed, the fuel cell energy could be used to recharge the propulsion battery. And of course, you can capture some dynamic brake energy and put it back into the batteries. But what I'm pointing out here, let's say that you have a half hybrid. It's 50% fuel cell energy or 50% fuel cell power and 50% battery power, roughly 1.6 megawatts of fuel cell and 1.6 megawatts of batteries. So you have a 3.2 megawatt locomotive, roughly 4,300 electrical horsepower. If the specific train, the route, the grade, you are running for so long that you actually draw down the batteries, once you lose the charge in the battery, you in effect regress back to having energy and power only from the fuel cells. So this kind of a 50-50 hybrid locomotive or whatever ratio you have, it may be it could become very route specific. Whereas with a diesel electric locomotive, again, the only constraint is how much fuel do I have in the fuel tank? And I can run over any route at any speed with any kind of train. And I have a relatively long distance and time to operate. So these are some factors to consider. Next slide, please. I want to point out that in 2020, last year, the report that you see on the left was issued. It was issued for Environment and Climate Change Canada. I participated in this on behalf of CAD Railway Services, the former Canadian Allied Diesel in Montreal, and other parties were Hydrogenics, which is a fuel cell subsidiary of Cummins Engine. Peter Eggleton, who I believe is on here for Intelligence Group, his consulting company, and the report was put together by Change Energy Services in Toronto. And the goal of this report for Environment and Change Canada, Climate Change Canada, was to come up with a potential way of converting a GP38-2 locomotive to a 50-50 hybrid fuel cell battery switcher. And one of the key things here that I think is very interesting, look at the graph in the lower right. The green line, you can see that fuel cells in general, the efficiency very quickly rises from start, but then it plateaus and starts to drop off. So fuel cells in general have a maximum efficiency at the lower power levels, whereas diesel engines, for example, the maximum efficiency comes at the higher throttle settings. So you have a situation where if you have a fuel cell locomotive in, let's say, a line haul or road application with a lot of energy being required, you could potentially be operating at less than the maximum capacity of the fuel cells. So these are just some of the details that will have to be looked at if and when we migrate toward fuel cell propulsion. Next slide. Another alternative, battery locomotives. And again, I am not criticizing, nor am I endorsing any form of alternative propulsion here. But the idea is to carry a large amount of electrical charge on board the locomotive. At the bottom, again, you can see that we could have compatible operation as with fuel cells, or to a limited extent with electrification. But we currently have no parts supply. There are no maintenance skills. Facilities, we probably could convert the diesel shops to maintaining electric locomotives, so I need to correct that statement. But there's no charging infrastructure, and charging of such large amounts of energy is going to impact grid connectivity, and there will be probably some grid energy pricing issues. The last sentence, maximum potential for recovering dynamic brake energy to be determined. It's quite possible that yes, we could capture a lot of energy going down long grades. But again, there are many areas where you don't have long grades in the US and Canada. And there are many situations where trains can go many, many miles without even touching the dynamic brake. So this is not a universally applicable process of capturing dynamic brake energy. So there needs to be a lot of research done here. Next slide. And operating range, I made an assumption here. Basically, you've got about 77 megawatt hours of energy available in 5,000 gallons of fuel. This is net of efficiency losses. You would get roughly the same 77 megawatts available at the rail for a fuel cell locomotive if you had a 16,000 gallon liquefied tender or gaseous equivalent. With a battery locomotive, given the same weight and size constraints as a diesel electric locomotive, you might be able to carry, I'm saying 7.2 megawatt hours, which will give you about 6 megawatt hours available at the rail. And with an electric locomotive, you're basically unlimited depending on how much energy you have from the grid. And is that energy available all of the time? So just some things to think about. Next slide. Capturing dynamic brake energy, yes. Diesel electric locomotive, right now we have no batteries to store that energy, so we waste it all to the atmosphere as heat. With a fuel cell battery hybrid locomotive, we could recapture dynamic brake energy to the extent that the battery on board has capacity to absorb it. With a battery electric locomotive, the same thing. Does the battery have sufficient capacity to absorb that energy? If it doesn't, you'll have to dissipate whatever excess energy you're generating as heat. With an electric locomotive, potentially, you can take most of that energy and you can pass it back into the catenary and pass it to other locomotives requiring propulsion energy, or potentially back into the grid. So dynamic brake energy recapture is a very good area that we need to look at, and there will be different forms of doing it and probably different extents to which it can be accomplished. Next slide, please. All right, we want to talk very quickly about refueling. I've got 5 examples here. You can look at this slide later. But my key point here was, even if we put in battery charging or hydrogen refueling at the stationary refueling, which is at the far right for each of these trains, the variable location, for example, of a distributed power movement, a distributed power locomotive, a DP locomotive, either in the middle of the train, toward the rear, or at the rear of the train, is going to impose some complexities. Let's move in the interest of time to the next slide, Emma. And again, infrastructure needed. The worst case I'm going to show you here is if I have to charge 32 6-megawatt battery locomotives at one time, that's the equivalent of charging 1,900 Tesla S autos. That's the energy demand equivalent of more than 6,000 US homes, or a small city of about 17,000 people. North Platte, Nebraska, where UP has the world's largest locomotive shop and locomotive yard, has a population of 23,000 people. So if I have to charge 32 battery electric locomotives, it's like adding about 2/3 to the population of North Platte, Nebraska. I'm pointing out North Platte for the reason of, let's go to the next slide. Here's some, basically I've looked at a satellite photo of North Platte. In the upper right, you can see what's referred to as the eastward run-through refueling, where trains pull in and the power at the head end is refueled, sanded, serviced, inspected, etc. And on this particular day, when this satellite photo was taken, there were 8 trains occupying all 8 through service tracks, a total of 16 locomotives. And at the rear of those 8 trains, farther to the west, were another 16 locomotives at different locations, depending on the length of the trains. So in all, we had 32 locomotives that could have been refueled with diesel fuel at any one given time here. So, you know, refueling trains is not as simple as simply pulling a locomotive up to a nozzle, a plug, or a hydrogen nozzle. Next slide, please. Okay, an electric locomotive, bottom line, you're depending on the grid, which is a massive infrastructure that has to be built. But again, I'm saying we have to look at what's the infrastructure for electrification versus the infrastructure needed for hydrogen, for example, or for supporting battery electric locomotives. And it's possible, in my opinion, that a straight electric locomotive could be equipped with a small battery, so that when you operate under a low clearance bridge, for example, prohibiting the installation of overhead catenary, you could drop the pantograph and operate on the battery through that low clearance zone. Simply pointing that out. And again, this all needs to be looked at largely through an economic analysis. Next slide. Some closing thoughts. Next slide, in the interest of time. Okay, hydrogen is green, but only in the future. The chart on the left, you can see the bottom line. Gaseous hydrogen produced in California from on-site electrolysis using solar or wind generated electricity in California has a carbon intensity of 11. For reference, the Air Resources Board in California says that petroleum diesel has a carbon intensity of 100. Hydrogen produced from methane reforming at the top. If it's produced from fossil natural gas and it's compressed hydrogen, carbon intensity is 125. If it's liquefied after being produced using steam methane reforming, your carbon intensity increases by 37%. So again, where and how is your hydrogen going to be produced? And there's relatively little being produced today. And the map on the right shows carbon intensity for the general electricity grid in each of the 50 states here in the US. And you can see it's very broad. It goes from almost zero carbon in Vermont to a high of 253, carbon intensity of 253 in the state of Wyoming. So this is why the grid, the generation of electricity needs to be greened. It needs to be more renewable from wind or solar. Next slide. Okay, well-to-wheel efficiency, a very quick look. These are my numbers. I've got 5 columns here. I'm assuming that you have in the top 5 sources of renewable electricity from wind, solar, hydro, nuclear, etc. 100% of your electricity is available. For an electric locomotive, by my calculation, ballpark, you get down to 89% effectiveness. You're losing about 11% in transmission and onboard conversion down to the traction motors. If you use that same renewable electricity to charge a battery electric locomotive, your well-to-wheel efficiency goes down to about 81%. If you use it to generate renewable hydrogen and then convert the hydrogen back into electricity on a fuel cell locomotive, your well-to-wheel efficiency may go down to 36%. I'm not factoring in any recapture of dynamic brake energy. And if you use that renewable energy to produce what are called e-fuels, Fischer-Tropsch fuels, where you take hydrogen and you take the hydrogen and convert it into a synthetic hydrocarbon with no carbon being released or carbon capture sequestration, your overall energy efficiency goes down to about 21%. So again, you need to look at all energy conversion. Every energy conversion process has efficiency losses, and these all have to be factored into the economics. Next slide. One comment about the industry, the locomotive industry. As you can see the slide in the lower, the graph in the lower right, there are no new locomotives basically being booked for production this year. This is the result not only of the pandemic last year, but also the massive changes in operating practice by the railroad. So we have an industry that demands somewhere between 0 and 1,450 locomotives per year. Contrast this with the heavy truck industry, where an average year is about 100,000 Class A trucks being manufactured every year. Locomotives are manufactured. These are large, very expensive machines as compared to less expensive trucks that are manufactured by an order of magnitude greater every year. Next slide, Emma. And we're coming to the end here. Recommendations. The first one, this is an industry issue, and the railroads and the suppliers have to be jointly involved. And I'm only going to touch on a few. We need regulatory harmonization between US, Canada, and likely Mexico as soon as possible. We don't have harmonization on various things in the safety world. Movement of hazardous materials, use of tenders, etc. We need to have harmonization because we are a continental rail industry. And the last thing I want to point out, two things. It's okay to build test cell, fuel cell locomotives or battery locomotives, test vehicles. But in the bottom line, we will have to have reliability growth testing fleets that will operate using pre-production lines, and I am not in favor of running around test tracks. Test tracks are great for accumulating mileage, but they are not the same as a real railroad. And my mantra here is, instead of testing, and buying, or rather, I want to test, and then buy, instead of test a little, buy, and then have to modify. And the last thing I'm pointing out, managers' misconceptions. Emma, please go to the last slide. These are 9 recommendations on the right. This comes from a book published in 1989. The man who wrote this book, Lowell Steele, was the staff executive for corporate technology planning at GE. This book was published in 1989. And many of the things in that the realities, many of these 9 realities are reflected in the comments that we just reviewed. Use only what's good enough. Pay attention to how past practice will limit the future. Watch out for Murphy's Law. Future unknowns are risky. The customer, the user, has to determine the value. New is not necessarily better. Here's probably the most important. Infrastructure is often the weakest link. You have to have standards, constraints, and routines, and a new technology and supporting and the supporting business systems must be jointly produced and installed. You cannot simply take a technology and drop it onto an industry. And that brings me to the last slide, Emma. And Tyler, I ran a little bit over what we were hoping for, but we still have 5 minutes of the scheduled time. Back to you. Thank you.
Well, thanks, Mike, for an excellent presentation and very timely here, given some of the research projects we were about to kick off on looking at deployment of alternative energy locomotives for the Department of Energy here and the Advanced Research Projects Agency Energy in collaboration with some other project partners who are on the call. So great presentation, very informative. We've had a number of questions come in, so I'll pose some of those to you just to continue the discussion. You went through a number of different potential locomotive energy strategies. In Europe, there's many hybrid freight locomotives that use more than one energy carrier or fuel. Is this a feasible solution to potentially solve the interoperability problem in North America? And but can we do that economically? And Mike, looks like you're potentially muted there.
sorry, there we go. One thing that's becoming increasingly common in Europe are dual mode locomotives, where you have, for example, a diesel engine, and it also has the capability to draw power off an overhead catenary. There are a number of dual mode locomotives operating on a commuter agency in the New York, New Jersey area, and they have twin diesel engines, and they can also operate off of overhead high voltage catenary. But the problem is that, you know, for freight locomotives, there isn't enough real estate on board the locomotive to have roughly the 4,400 horsepower diesel engine and also have the large step-down transformer. So the technology is feasible, but this points out some of the differences between solutions in Europe, for example, and solutions in North America. And you touched on this at the beginning when you referred to heavy haul railroading, which is primary here in North America and in certain areas of the world, such as Western Australia. So there are technologies that are out there being used, but again, the limitation becomes the space and volume and weight constraints here on North America.
Thanks, Mike. So one of the other things you mentioned was, and you mentioned this several times, that this is a industry-wide issue. Is there a role for the AAR, or the Association of American Railroads, to help promote standardization or common approaches so that we don't wind up with each of the big railroads going off on their own and dividing the rail industry?
Right. Well, and of course, again, yes, the AAR, the Association of American Railroads, is the trade organization for almost all of the railroads. For the Class 1s, the American Short Line Railroad Association, for Amtrak in the passenger world, for many of the commuter agencies that operate rail equipment and so on. So it's the logical place, I think, to centralize discussions, planning, and efforts to move ahead. But you also mentioned the ARPA-E, Advanced Research Project Agency from the Department of Energy, the ARPA-E project to develop an economic model. And that's something that probably needs to be supported, but also guided to make sure that you know, as many assumptions and as many alternatives are included in the analysis, and we don't end up prematurely disposing of certain technologies or pre-favoring some and disposing of some prematurely.
Well, definitely, and for our part in that project, we definitely hope to engage the industry and as a stakeholder group in advising our research. You mentioned just briefly the Short Line Association, and one of our questions is, you know, how does this challenge apply to short lines who have a much different, you know, economic and operating model than the large Class 1s?
Good question. And again, you know, the short line railroads are an integral part. Short line railroads and switching companies, which are technically legally, you know, not short line railroads, they are an important part of the rail network. One of my clients happens to be Anacostia Rail Holding, which owns Pacific Harbor Line. PHL is the operator of the rail network in the ports of Los Angeles and Long Beach. The rail network in the ports is actually owned by the two port agencies, and PHL is the switching company that moves trains around on those port tracks. PHL is scheduled, it's been announced publicly, PHL is scheduled to be getting a battery electric switching locomotive later this year to supplement its fleet of diesel electric locomotives. And that's an example of a switching company that's looking at zero, at least on a point emission basis, a zero carbon locomotive as a point emitter. It's been announced, for example, that the Sierra Railroad in California is going to be converting a former Union Pacific Green Goat battery diesel locomotive to a fuel cell locomotive. And CP, of course, has several fuel cell projects that have been announced. But again, there are thousands of locomotives operated by the short lines and the switching companies and by private industries, well above the 25,000 locomotives that are reported by the AAR for the Class 1 railroads. So this is an important area of the industry that ultimately is going to have to be addressed.
That's excellent point, Mike. A couple of questions here related to operations. The first is, we've had a lot of changes in our railroad operating model over the past few years related to asset utilization, and what changes coming forward might we see that could allow for heterogeneous locomotive energy technologies and potentially swapping out locomotives and interchanging them, what might we have to rethink on the operations side?
Well, as I pointed out with, what I referred to, I described it as a hypothetical railroad. The industry and individual railroads, particularly the Class 1 railroads, are going to have to look at the economics of all the alternatives and do a deep dive and an honest, unbiased review of the economics and, how do different alternatives fit the network model, how we operate trains, how we run power through terminals versus swapping out power and going from one mode of propulsion to another, in effect, kind of regressing back into the steam era. But are the economics overwhelmingly in favor of doing that as opposed to having a one-size-fits-all solution, which may, and I emphasize the word may, result in sub-optimized economics and making the overall decarbonization effort less effective than it really could be. So it's really the economic analysis and how do the technologies fit with your model of how you operate your railroad and how you potentially could or should have to operate it in the future. It's a big unknown.
Definitely, and another piece of the economics is, as you know, hauling a number of these fuels, particularly coal used to generate electricity, is a big source of traffic for the railroads, and ethanol and now even crude oil and, as well. As we head down this decarbonization pathway, what are the implications for the railroads from the sort of traffic and operating side, and how's that going to affect our railroad industry?
I haven't even looked at that, and I'm not going to make any prognosis here in terms of what's going to happen. Obviously, if the effort is to eliminate the use of fossil fuels, that would mean eliminating the use of fossil petroleum as we know it today. But again, many of these plans include the generation of synthetic fuels if you can afford to use them. And so, there will likely be liquid substitutes for petroleum fuel, for example, that will still need to be produced and transported. So that's another aspect of the overall picture here that needs to be assessed by the industry.
I got three more questions here. A couple on two technology questions, then a real broad one I'll save for last here. First one is what about self-propelled rail cars or more distributed electric battery power over sort of a multiple unit type distributed on different rail cars or self-propelled rail cars? Is that something that we might see in the future, or is that sort of still a science fiction idea?
Well, it's I'm glad you brought it up. I've actually been myself, I've been quietly to myself pondering, the idea of, is there some applicability in our industry for the future where we may, instead of operating freight trains with large amounts of locomotive power at the front, at the middle, and at the rear, and 20, 30,000 ton or even just a 5,000 ton freight train, we have small trains that are dedicated to priority freight. I'm not going to discount it. I don't know if it would be feasible for railroads to do it, but I think one thing we need to keep in mind, we have a symbiotic relationship right now, railroads and the trucking industry, in terms of that the railroads support the trucking industry for long haul movement of trucks and containers. There's a general number, I think somewhere around 700 miles I've heard, where if you're talking about more than 700 miles economically, it may be favorable to move your trailer or container by rail. With the changes that are coming with truck efficiency and so on, that trade-off distance may be shifting in favor of truck for longer hauls, which means that the whole competitive nature of truck versus rail may be changing here. And so, there's a number of things that need to be looked at here. And this whole idea of call it a new generation of trains, so to speak, it could very well have a place in our future.
Very interesting comments. And so, second technology question here is more in the immediate short term. What's the role of diesel electric propulsion and the tier 5 in the short term? Is what's the pathway there?
Well, there are 25,000 diesel electric locomotives registered by the Class 1 railroads. And again, as I mentioned, there are no reported deliveries of new Tier 4 locomotives this year, either line haul or switch locomotives. And that's because most of the Class 1s have large numbers of older line haul locomotives, mostly line haul locomotives that are stored. I saw something this week that one railroad has more than 2,000 locomotives in storage right now. Again, this is due to the impact of precision PSR management changes in how the railroads operate, as well as there's still some traffic impact from the pandemic. But the railroads have certainly learned how to operate the old level of traffic with fewer locomotives, as well as fewer employees, fewer assets, sweating the assets even harder. There's definitely a place for the existing locomotives going into the future. One of them is with perhaps using more biodiesel, go into a B20 blend, where you will reduce your carbon production by using 20% biodiesel. But again, your PM will go down, your NOx may go up slightly, but your energy bill might go up as well, because volumetrically you're going to have to use a larger amount of B20 blend as compared to moving 100% petroleum diesel with a higher energy content per volume per gallon of fuel. So there are trade-offs here. But this does not mean that we should scrap our locomotives today. First of all, we have no replacement for them, but we need to start looking ahead here at this transition period. The next, in my opinion, the next 9 years to 2030 are going to be critical. We need to start assessing the alternatives and testing them, and rigorously testing them in real world conditions, so we get a handle on how realistically can we make them, how realistically can we maintain them and operate them, and the safety of the technologies and the economic results. And then, the big long climb from 2030 to 2050 to actually decarbonize and get ourselves down to actually zero criteria emissions as well.
Well, that's a great segue for the last question here. It's kind of a big one. Who do you think should take the lead in conducting and paying for all the research and development required to improve the fuel efficiency and decarbonize the rail industry?
Well, I'm going to ask a pointed question. Do you pay taxes, Tyler? U.S. taxes?
I definitely do.
Okay. I think most of us pay U.S. taxes, and as such, we fund the federal government. Now, obviously, going back to my slide, by the conclusion of the Super Truck 3 project, the federal government will have contributed over $300 million to cleaning up and going zero carbon with heavy duty trucks. It would be nice to get some funding from the federal government, but the federal government, DOE in particular, I think the attitude is they will put their money where they can get the biggest bang. And the biggest bang is out of the 60 some billion gallons of diesel fuel consumed here in the US, 40 billion is consumed by heavy duty trucks. The other 20 plus billion gallons is consumed by agriculture, construction, etc. So the big bang of investing in reducing diesel fuel usage is obviously for Class 8 heavy duty trucks. That's what's governing where the Department of Energy is putting its money. Is there a chance for the railroad industry to get some funding from the federal government? Possibly. You have to ask. And I know it's been requested. There have been requests made before, but obviously we've not had much success in that area. So I think that's the most likely area. Is it? What's the probability that we will get funding? I don't know. I don't have enough batteries in my crystal ball, or I think in anyone's crystal ball, to really say what the probability is of getting it.
All right. Well, thank you very much, Mike. There's a couple other specific questions, but we can forward those to you to answer offline. Thank you again for a tremendous seminar, a lot to think about, a lot of great information, and always learn things when we talk to you. So thank you very much for your seminar. Thanks for everyone who attended online. Remember, if you want your professional development hours, please send an email to the address that was in the seminar announcement. And we look forward to seeing you again back in the fall when we pick up our seminars for the fall semester. Watch for email updates on those as we plan them. With that, enjoy the rest of your day. Have a great weekend and stay safe out there. So thank you very much.
Thank you.